morning everyone. Today we are going to see about feedback linearization of robotic manipulators. The organization of this lecture will be as follows. First we see the feedback linearization approach and then we apply that to robot manipulators, both for kinematics based control as well as dynamics based control. Let us start. Feedback linearization. So, what is that about? It is about if the closed loop system dynamics of a non-linear system becomes stable and linear through a suitable control law, then this approach is termed as feedback linearization. If the closed loop system dynamics of a robotic system, say for example tau equal to m of theta into theta double dot plus c of theta comma theta dot multiplied by theta dot plus g of theta is a system equation, which means it is a highly coupled nonlinear system dynamic equation for a n degrees of freedom robotic system. If this system representing the robotic system equation representing the robotic system n degrees of freedom robotic system by a suitable control law becomes stable and linear, then we can say that we have feedback linearization approach being applied to the system. In fact, there exists a class of nonlinear systems. There exists a class of nonlinear systems for which feedback linearization can be applied. Approach can be applied. Let us consider a class of, single input affine nonlinear system given by d by dt of x1, x2, x3 up to xn minus 1 and xn is equal to x2, x3, x4, xn f of x plus g of x into u. Let this be represented by equation number 1. So, we can say that the output equation is given by y equal to x1, it is equation 2. Assuming that with the assumption g of x is not equal to 0. So, which implies that g of x is invertible. Okay. So, if we choose the control input given by u equal to minus 1 by g of x multiplied by minus f of x plus kvr plus lambda 1 multiplied by e power nth derivative plus continues lambda n minus 1 first derivative of the error plus we have x n t, where I mentioned error E is given by y desired minus y actual. E is nothing but output tracking error. More precisely, it is called E equal to y desired minus y. Y is the actual output of the system and y desired is a desired value for the system, and yd minus y is the tracking error. And let us consider r equal to E of n minus 1 derivative plus lambda 1 E of n minus 2 derivative plus lambda n minus 1 E. So, I indicate that E dot is represented by e power 1. So, the power indicates the derivative. So, the closed loop system dynamics, precisely the error dynamics, the closed loop error dynamical equation for this case becomes r dot equal to minus kvr, which is linear as well as stable by choosing kv as positive. So, kv and lambdas are positive design parameters for the feedback linearization control approach. Thus, such technique is called as feedback linearization approach, which stabilizes the closed loop system dynamics. Now, let us consider an example in the fresh page. Example 1. Let us consider a single link robot manipulator whose dynamical equation is given by tau equal to ml square q double dot plus bq dot plus mgl sin q is given by this equation number 1, where q is a generalized coordinate of the robot. Here we have a single link robot manipulator where the joint angle or the generalized coordinate is being theta here. It is a revolute jointed robotic system, and the system parameters m equal to mass is equal to 1 kilogram, length of the robot being 1 meter, and we have the acceleration due to gravity given by g equal to 10 meter per second square, with b value which is the term responsible for Coriolis and centrifugal forces, that is taken to be 0.1. So, for this system the question is, design a control law that would make closed loop error dynamics linear and stable. Design a control law that will make the closed loop error dynamics linear and stable. Let us see that now. So, the solution to this case is, it is desired that the manipulated tracks here desired joint angle. So, objective is to track a desired joint angle given by QD, and let us describe or define the error, so called tracking error, being E equal to QD minus Q desired angle minus actual joint angle of the robotic system. This will be equation 2. Let the control law be chosen as tau equal to A multiplied by QD double dot plus KDE dot plus KPE plus BQ dot plus C into sin Q. Let this control law be represented by equation number 3. Next, we can see in the control law A represents ml square, that is the mass matrix you can say, and C represents mgl part. So, now replacing now with this control law of tau, let us replace the tau expression in the actual system dynamics that is given by equation 1. So, we get A q double dot plus B q dot plus mgl sin q is equal to A multiplied by QD dot single dot plus KDE dot plus KPE plus BQ dot plus sin Q multiplied by C. Okay. So, this is the situation. Now, we can say that this can be equation number 4. So, thus equation 4 is going to be reduced. Okay, so, you can see that upon simplification equation 4 turns out to be a second order aerodynamic equation given by E double dot plus KDE dot plus KP into E equal to 0, which is equation number 5. Thus, the closed loop aerodynamics is linear and stable as well for positive values of the controller gains Kp and Kd. Okay. So, that is a situation here. Okay. So, we have finished the first example in this case using a dynamic model of a robotic system. We can now move into feedback linearization control approach towards kinematic model of a robotic system. We now have a kinematic model of a robotic system, which starts from x equal to f of theta. What is that? It is forward kinematics. So, x dot equal to j theta dot, what is that? It is differential kinematics. So, from this we can, from equation 2, that is differential kinematics equation, we can say that theta dot equal to j inverse x dot. Okay. So, now this is a situation called inverse kinematics. As I mentioned earlier in the lecture, that inverse kinematics is for controlling a manipulator. Let us see that. Let us consider the control law for this system x dot equal to j theta dot. For this nonlinear system, when we consider a control law, so that nonlinear system becomes, the closed loop aerodynamic equation becomes linear and stable, we can say that the control law is a feedback control law, and this approach is a feedback linearization approach. So, let us choose a control law. Control law which is given by theta dot equal to j inverse multiplied by kp times error plus x d dot. Okay, so, this is the control law. Let us choose this control law, theta dot equal to j inverse into x d dot plus kpe. Now, what happens here? When we substitute back into this equation, we get x dot equal to j multiplied by j inverse into kpe plus x d dot, which leads to the first order aerodynamic equation, which is given by E dot plus, so you can have this capital E dot plus kpe is equal to 0, where E is equal to x d minus x. That means desired Cartesian portion of the end effector, and x is actual Cartesian tip position of the robot. Similarly, E dot becomes x d dot minus x dot. Upon substituting back, because we know that theta dot equal to j inverse x dot, that theta dot is given by the control law, that is j inverse into x d dot plus kp into error. So, let us equate this to this equation, which is j inverse x dot, and this turns out to be E dot plus kpe is equal to 0, which is nothing but a first order error dynamic equation, which is E dot plus kpe is equal to 0, which implies that E tends to 0 as time tends to infinity. Okay. So, depending on the positive values of kp, we can ensure that E tends to 0. Now, let us talk about an n degrees of freedom robot manipulator, whose dynamic equation is given by tau equal to m of theta multiplied by theta double dot plus c of theta comma theta dot multiplied by theta dot plus g of theta, where tau is the n cross 1 joint torque vector, and theta double dot, theta dot and theta are nothing but n cross 1 joint angular vector, joint n cross 1 joint angular velocity vector, and n cross 1 joint angular acceleration vector. Joint angular acceleration vector, theta dot is joint velocity vector, and theta is joint angle vector whose individual sizes are n cross 1. And what is m of theta is a n cross n matrix called mass matrix or inertia matrix. And C of theta comma theta dot represents Coriolis and centrifugal matrix which is of size n cross n, and G of theta is a n cross 1 gravity vector. Now, as per equation 1, we have the system dynamics given by this equation which is highly coupled for a n degrees of freedom robotic manipulator. Now, we choose a control law. Choose a control law. Tau equal to alpha tau dash plus beta, as we have seen in the previous class, model based control strategy for robot manipulators. We have chosen this control law tau equal to alpha tau dash plus beta as the control law, where alpha equal to m of theta and beta equal to c of theta comma theta dot into theta dot plus g of theta, and tau dash is nothing but the servo law which is given by theta d double dot plus kpe plus kd e dot. Again tau dash is nothing but the servo law which is given by theta d double dot plus kp multiplied by error plus kd multiplied by error dot, where error equal to theta d minus theta and error dot equal to theta d dot minus theta dot. Now, substitute the control law chosen tau equal to alpha tau dash plus beta with what is tau dash and alpha and beta, substituting back in this control law, we have one huge expression. Let that expression with the values of tau dash, the expression of tau dash, alpha and beta substituted back to the control law, let that equation be equation number 3. Now, substitute equation number 3 back in equation 1. Equation 3 in system dynamics 1, we get alpha into theta d double dot plus kpe plus kd e dot equal to m of theta into theta double dot plus c of theta comma theta dot into theta dot plus g of theta. Here the beta is c of theta comma theta dot into theta dot plus g of theta. This represents the beta value. This represents the tau dash value. Okay, and then alpha can be replaced by m of theta. So, this equation is going to be turned out to be E double dot plus kpe or kd e dot plus kpe is equal to 0. That means we come out finally with the second order aerodynamic equation upon substituting the chosen control law back into the system dynamics. Thus, the closed loop system dynamics becomes the second order aerodynamic equation which is stable and linear. So, with this I come to the conclusion that in this lecture we have seen the design of feedback linearization where the chosen control law u can be substituted back into the system dynamics in order to make the closed loop system dynamics linear and stable. We have seen feedback linearization design, and then we have seen an example involving 1 degrees of freedom single link revolute jointed manipulator, 1R manipulator. Precisely it is a planar manipulator. We have seen applying the control law, and then we have seen kinematic control of a robot manipulator using feedback linearization with the control law being theta dot equal to j inverse into x d dot plus k p into error. This is basically the control law with the common and popular nomenclature CLIK, closed loop inverse kinematics, which makes sure that given a desired trajectory like this, your actual trajectory with the error between the desired trajectory and the actual trajectory in the Cartesian space can be taken into account by the control law given by CLIK. So that during the inverse kinematic process, you will have the desired trajectory here, and your actual trajectory will also be merged or tracking the x d of t more accurately. That accuracy is ensured by the term Kp, which is a positive definite matrix value for an n degrees of freedom robotic system. So, we have seen how feedback linearization is implemented for a kinematic model based robotic system control. Then finally, we have seen the feedback linearization control approach for a n degrees of freedom robot arm, where it has n degrees of freedom, which means that n links you can say and n joints. For such system, we have used the control law tau equal to alpha tau dash plus beta. We have used this control law in order to have the closed loop system dynamics being stable. So, as I mentioned, for the kinematic control, we had E dot plus KPE equal to 0, first order aerodynamic equation. For the dynamic model based control with the feedback linearization, we eventually ended up with second order aerodynamic equation. That is a difference between applying feedback linearization for kinematic model based control of a robotic system and a dynamic model based control of a robotic system. So, with this I stop here, and you people can try solving 2 degrees of freedom robotic system, which is R and R planar robot. You can try solving by computing the dynamic model. If you have the dynamic model of the simplest 2 degrees of freedom revolute jointed robotic system, which means x, this is y. If you have this one, this is theta 1, theta 2, and this is L1, L2. If you have such a 2 link planar manipulators dynamic model, you can try that by having the partition controller tau equal to alpha tau dash plus beta, and try to have the trajectory for both theta 1, theta 2 matches perfectly. That is all. That is theta in degree, time in second. Okay, that is all. I stop here. Thank you very much for your patience. The next class we will see about Lyapunov stability theory, followed by robot programming. Thank you very much.